My name is Mark Senti, CEO of AML. Today we're going to talk about the future is now, radical changes in aerospace and transportation. No better place to start talking about transportation than where we are today. Many of you may recognize LA and Highway 405 in the middle of the day. And at night, it looks something like this. You may call it a roadway. It's actually a parkway. In other parts of the world, it looks like this today. Here is Mexico City. And I mean today. Here's an article from just 2 days ago, May 14th, and actually a place I will be next week where people are required to stay indoors because of the pollution. Where's that pollution coming from? From the 25 million people and the cars that they drive, which are all powered, of course, by gasoline. But let's see how we got here. So let's go way back to the 1800s where it all started, and where we started with the term horsepower. The horse pulling the carriage. We then took the horse and we attached it to rail. We then took the invention of the steam engine and we put the carriages on the rail, and we're able to also use steam engines to power our ships. And then in the early 60s, we took that steam engine and we created the great Union Pacific Railroad. The iron rails, the Iron Man, and they had a slogan back there, the Union Pacific Railway, the short, quick, safe line to all points west. And at this end of this presentation, we'll see what the future of rail looks like. Then in the 1990s, because of Henry Ford working on his quadricycle and his back shed, he created the first automobile powered by pure ethanol. And shortly after that, in 1903, he formed the Ford Motor Company, which was not just the beginning of cars for transportation, but the beginning of factory automation. So here we are today. These are the various forms of transportation, from cars to rail to buses, etc. And again, all of them powered by fossil fuels. And all of these transportation using gasoline and diesel. And I think it's really, really important that as we understand that, we also have to understand our fuel sources and what components relate to our actual energy. As we know, energy is what drives everything, including transportation. So if we look on the left-hand side here, we see that transportation in this chart represents 29% of the energy used in the US. On the other chart, of that energy used for transportation, petroleum or gasoline represents over 55% of the energy sources used for transportation. Now, if we look at the total energy flow, and this is a very busy chart, and what we have on the left-hand side is all of our inputs. So we have coal, natural gas, crude oil, petroleum, etc. And on the output is our various forms of use, including residential, commercial, industrial, and transportation. And transportation represents close to 30% of the usage of our energy flow. So what are we transporting? We think about transporting ourselves to work, to school. Actually, 835 times more stuff is moved annually than the combined weight of all Americans. So most of what we're moving is cargo. And the vehicles we're using, 63% of all transportation, modes of transportation, are cars and trucks. And if we look at energy and transportation, and we look at it in respect to the consumption again, we look at residential, we look at industrial, we look at commercial. Transportation itself, in terms of its input for energy, 92% of the energy used for transportation today is petroleum, and only 5% for renewable energy. So again, here we are today. We have this issue of pollution, we have this issue of traffic, all kinds of challenges with transportation. So where do we go from here? What is the solution? Well, the solution is simple. Eliminate gasoline and diesel. Do you believe that? We'd say goodbye to internal combustion engines, and we'd say hello to electric motors. Do you believe that's going to happen? Well, you may not have a choice. This is a really interesting slide that looks at various countries and associated cities in terms of where they're going with fossil fuels. And what's most interesting to me is if you look at countries such as France, who has a mandate by 2040 to eliminate all gasoline diesel, a city within France, Paris, has a mandate for 2025. So you're going to see a combination of both countries and cities within countries that establish these mandates where you will not be able to purchase any type of fossil fuels for transportation. So it's an end of a legacy. The great Henry Ford, the first engine there on pure ethanol, and for some of us, this is my last combustion engine. My next vehicle will be driven by something other than fossil fuels. So, virtually all transportation is going electric or hybrid electric, and based on that, all the major automotive manufacturers are ceasing the end of the development of nuclear internal combustion engines. They're going electric. So it's Volvo, it's GM, it's Mercedes. And what's very interesting here is that when people think about electric cars, for example, they think they're going to be giving up something, size, luxury. No, it's not just big. This is downright electric, as you see here from the CEO of Mercedes. But hey, electric cars have actually been around for a long time. Actually, back in 1932 was the first electric carriage. And if you look at 1990 and you looked at the makeup of automobiles, of the 4,000 cars produced in the United States, 28% were electricity, and 1/3 of all cars found on the roads in New York City, Boston, and Chicago were electric autos. Now let's take a break and let's talk about AML, and let's try to understand the relevance of AML, the Advanced Magnet Lab, in transportation. Well, first of all, magnets really matter. In fact, if we didn't have magnets, our world would look like this. It'd be completely dark. Without magnets, we would not have electrical generators. We would not have electricity. Furthermore, without a magnetic field, which protects us on Earth, we would be bombarded by cosmic and solar rays. So the magnetic field protects us from radiation. So magnets enable generators. Generators enable electricity. So when you look at a generator, I want you to think of a magnet. But a generator is also a motor. And motors, what gives us water, which gives us manufacturing, which gives us farming. Magnets gives us all types of modern day conveniences such as appliances. We have cars, we have robots, all driven by magnets, including our smartphones and our laptops. So back to transportation, and let's talk about electric. Today, we have various vehicles that are electric, and tomorrow, as I mentioned before, most all vehicles will be electric. It's something we call e-mobility. E-mobility is the electrification of transportation. And for all of these hybrid and electric vehicles, they all today are, and in the future, the new vehicles are driven by motors. And as you saw in the previous slides, if you look at motors, which propel e-mobility, motors are made up of magnets. So magnets are the beating heart of motors and e-mobility. So if we look at electric propulsion, there's really just two components. And what do we hear about all the time when we talk about electric cars? We hear the biggest constraint is batteries. Their power density, in other words, how much power per weight, and also their cost. So it's batteries. But wait a minute. Where does virtually all the energy go from those batteries? It goes to motors. So just like batteries, motors have a similar situation. We would desire to have the highest power density, so the highest power at the lowest weight and the most efficient. And what did we say motors are? Magnets. So our company is involved in the development of applications all based around magnetics. We work with startups, Fortune 100, Global 2000 companies. It's all based on a technology platform that we developed, which encompasses very advanced software, very advanced magnet technologies, and manufacturing technologies. And our business model is very similar to companies you might know, like Intel or like Apple, is we may not be the final product, we may not be the motor company, but we want to have the magnets inside. And very much like Apple, Apple designs your phone, they sell you your phone, but they rely on somebody else for the high volume manufacturing. And that's the same with AML's business model. Now, as you will see on the next slide, AML has very, very diverse experience across all sectors. But because of what's going on in transportation and way beyond cars, which we'll get to in a minute, AML is laser focused on e-mobility and bringing to market very, very advanced magnets, which at the very top level, significantly improved the performance and cost of motors. And here's the slide I mentioned before to also just remind you of all the sectors and all the applications that are impacted from magnets. But we're going to focus on e-mobility, and the motivation behind that was actually working with NASA for over 6 years in developing very sophisticated software which would try to address these very, very high power density machines for large aircraft. And it was using something that's very complex, something we call superconductivity. And we won't go there, but we will say, just like Airbus, we came to the conclusion that superconductivity was just not going to get us there soon enough. So that was the motivation and then the genesis behind of the very breakthrough magnet technology that we developed, which we'll be introducing. Our team is made up of world-class scientists, both in the area of superconductivity and magnets. So what are the challenges of electric propulsion? Well, as we stated earlier, all of these vehicles require electric motors for propulsion. And these motors desire to have the highest power to the lowest weight, something we call power density. In many cases, we also need very high specific torque. And one of the reasons for that is that future aircraft, which we'll talk about in a moment, that are electric, they are unable to use gearboxes. It adds complexity, but because they're directly attached to a propeller ducted fan, they're very limited in their RPM, and so you need very high specific torque. Now, most of these motors use permanent magnets for the rotor. What is a rotor? If you look at a motor, it's made up primarily of a rotor which spins, which is made of permanent magnets, and a stator, or an armature, which is made of copper magnets. And these permanent magnets, 90% of them are produced in China. Now, furthermore, these permanent magnets, when they're produced as individual little pieces, sometimes larger pieces, are very, very dangerous. The magnetic strength is so strong, you have to be extremely careful when you handle them. And if you don't believe me, ask this guy. He actually lost a piece of his finger when he was dealing with these permanent magnets made of what we call neodymium iron boron material. So as I mentioned before, a motor is made of a rotor and stator, and the whole goal with motors in terms of having performance is to have the highest magnetic field between that rotor and the stator, something we call the gap. And if you look at how motors today are designed and built, something we call a conventional north-south pole configuration, and you look at this chart, you can see that 50% of the field is not going where you need it. So in order to compensate for that, these motors incorporate iron and steel, which increases the field, it saturates it, and tries to better concentrate it. Where? In the gap between the rotor and the motor. Now, there is a very unique and nice way that you could improve that. You could arrange the magnets in such a way with different magnetic field directions that you could increase the field between the motor and the generator. Unfortunately, in order to do that, it's extremely expensive. It's so expensive that nobody does it. And that configuration is something that's known as a Hallback array, named after Klaus Hallback, who invented that in the late 1970s. Well, AML has solved that problem and a lot more. As I mentioned before, all the magnets are made in China. It's a very, very laborious and dangerous process. It's done in a way where people have to work inside what's called glove boxes, so they're limited in their throughput, they're limited in their size and the scale, and they're also dealing with environmental issues. And only in China can you find labor that's 50 cents per day and be allowed to manufacture and be so little concerned about the environment. So what AML has come up with is a completely novel way to produce permanent magnets. It removes the labor, it increases the yield between 10 and 30%, it allows you to make unlimited lengths, all different types of shapes and sizes, and then magnetize them in a very, very optimum way. That's something we call PM wire. If we take that PM wire and then we configure it into a configuration that's ideal for a motor, in say a ring or a helical geometry and more, and we magnetize it in the most optimum way, then we can put all the magnetic field where it needs to be in the gap, in the right configuration, without any steel or iron, which reduces the weight. And this is a figure here showing those two processes that come together. Now we're talking about permanent magnets, but it turns out in order to produce a permanent magnet, you have to somehow magnetize it, and then it stays magnetized forever. And in order to do that, you need very unique electromagnets, which is also part of AML's intellectual property and patents, so that we can produce this very, very optimum, pure magnetic field embedded in a permanent magnet. And so that's what you see now, comparing what we call a PM360 product compared to conventional. For many applications, we are replacing dozens, and in some cases hundreds of individual magnets with one single magnet. So that reduces the cost, the complexity of assembly, and oh, by the way, we have the optimum field there. You see an increase of the usable field by over 50%. So what does that really mean to a motor? Well, let's take a look at a few examples. If you look at a very, very small motor, a drone motor, something that is only about 22 millimeters in diameter, if we simply just replace what you've come to know as this conventional north-south segmented magnets, as you see on the left-hand side, with one of our PM360 rings, and without making any other changes to the motor design, we get an improvement of approximately 10%. If we do make some changes to the other end, that stator end we talked about, the copper end, we can have increase in performance of upwards of 30%. If we have the opportunity to apply two of our PM360s, something we'll call a dual rotor, in new machines, then we have the ability to increase the performance somewhere between 30 and 50%, depending on the application. And here's an example of the plug-and-play replacement, removing the old magnets and replacing them with a PM360 in a format of a ring. And for drones, what does that mean? It means you can either fly further, fly longer, or lift more. And this is just an example of case studies by some of the leading drone companies in the world, where they've given us their dream specifications, their dream desires, which could be less mass, could be more efficiency, could be more torque. Depending what they are, we analyze it through our software and understanding what our PM360 product and how it performs. And these are an example of some of the results. And similarly, this will happen for EV. We're just beginning to engage with major players in the electrical vehicle market. This slide shows you here that the Department of Energy, which has come out with a very comprehensive plan for electric vehicles, which addresses batteries, power conversion, and of course motors and all kinds of other attributes that lead to the cost and efficiency of electric vehicles, have set the bar, set the benchmark to try to achieve in terms of the power density for electric vehicle motors. And using our dual rotor configuration and our PM360, we see that we can very, very easily approach their near-term goals, and we're very optimistic about their long-term goals, which are very, very aggressive. So let's talk about e-mobility and beyond just electric vehicles. Of course, we have trains today. We mentioned all kinds of different cars, and the reason for cars are some of these elements. When you talk about any type of energy or electrical energy, you're always converting, everything gets converted to heat. So the more you can turn that into work, the more efficient it is. And when you look at energy as a total component, electric cars are 95% operating efficiency of electric motor. That's really good. Fuel waste of 70 to 80% of energy is heat and wearing out parts. So this is just a comparison between hydrogen combustion engines and electric. And it's not just Tesla. We hear a lot about Tesla, but looking at electric cars, as we mentioned before, everybody's in the business, and you can see Mercedes' commitment there around the world. Companies like Volkswagen investing upwards of $19 billion into electric vehicles. And what's unique about transportation today when you go electric is the business model change. If we remember Henry Ford, most of the focus was on the engine. And once you remove that engine and you replace with electric motors, now you're just focused on the battery and your simple drivetrain. So companies like Volkswagen are actually going to make available and license the actual chassis to other people. So you can buy the chassis with the battery and the motors and make your own, the rest of the car as you see it. And of course, all kinds of nice features with all the new cars coming along. You will not be deprived of anything when you go from gasoline to electric. Again, it's not just Tesla. Who knows Dyson? They make vacuum cleaners, they make hand dryers, they make hair dryers. Matter of fact, Dyson produces over 65 million motors a year, over 5,000 engineers, and guess what 500 of them are busy doing right now? And guess what product they're going to introduce around 2023? Their own electric vehicle. So even Dyson is going to be in the business. Of course, there's many, many rumors about Apple. They've been working on this for some time, Project Titan. And then it's not just big companies. Rivian Motors, who introduced a four-wheel drive truck, 0 to 60 in 3 seconds, 400-mile range, along with a full-size SUV with the same characteristics. This company, or this car company, was started by R.J. Scaringe, who today is 36 years old. Once he introduced this at this auto show, he immediately had Amazon come in to lead a $700 million round of investment. He had GM jump in, they jumped out, somebody else jumped into the game, and here's Ford again. Ford's in the business. And here you can see an announcement of a $500 million investment into RJ's company for them to work on, similarly to Volkswagen, with the actual drivetrain platform for Ford's electric vehicles, at least probably for their trucks. So that train has left the station. Everybody's in the business, whether it's the high-end sports cars or the lower-end small cars, they're all headed to electric. And China is certainly way ahead of everybody. As you can see, there are over 487 car manufacturers. The company you see on the far right side there, which is NeoEve, the founder of that company, he states very clearly that he's not creating a car company. He's not a car company. He's a lifestyle company. And that's kind of the theme you're going to see with new transportation. It's all about the lifestyle and not necessarily the horsepower. And of course, it's not just cars, it's also trucks, soon to be maritime, beyond just the diesel power generation to electric, but getting into more fully electric, hydrogen, all types of other energy sources. So who knows what type of electric vehicles you're going to have? Of course, e-bikes are becoming very popular, scooters, etc. But when you go electric, you have all kinds of interesting opportunities for vehicles. So let's talk about aerospace, the future of aerospace. And when I talk about the future is really now. And here's where you're going to see the real radical changes. Going from an internal combustion engine in a car to electric, yeah, it's more efficient, less noise, but the car is principally the same. A lot is changing in aerospace. So let's start with something you're familiar with, the smallest of the aerospace vehicles, if you will, something called UAVs or drones, an industry that's growing exponentially for delivery, inspection, emergency service, agriculture, construction. The applications for drones are endless. I hear people talk about, they sit down and they start to write on a piece of paper how many applications they could come up with drones. And once they get over 50 or 60, they realize that it's almost unlimited. You may have recently seen in the news that UPS has made their first blood delivery, and the University of Maryland made their first kidney delivery, so organ delivery. And Google now is getting approval to begin their drone delivery service. And of course, the military is probably one of the biggest purchasers of drones out of all markets. And those range from very large drones, which you see in the next slide, to these very, very small drones, which gives every soldier a whole new set of eyes and tools to do their job. But of course, with most technology, there's a downside. So the Army is actually worried about the military being bombarded by drones. I've talked to other people that have unique applications in terms of these swarming drones, with the idea to have drones that can carry 50 gallons of water. And so when you go to a forest fire, you attack it with hundreds of drones versus a helicopter and a big, and a 500-gallon supply of water. And the military, as I mentioned before, is a very, very big user of drones. Some of them are very large. They're basically unmanned jets, but the military too is headed towards hybrid electric drones. And we'll talk about that hybrid electric in aircraft in a moment. So just like automotive, aerospace is in parallel in terms of its path and for many of the similar benefits. So when we talk about e-aviation or electric aircraft, there's two types. One is fully electric, similar to cars, where you have enough battery to get whatever your cargo is to the distance it needs to get before recharging. But for the larger vehicles, the larger aircraft, where you have more cargo or more people and you have to go a further distance, you have electric propulsion, but you also have onboard power generation. But it turns out in even a large aircraft, something let's say 160 passenger aircraft, it's more fuel efficient to burn a fuel into a turbine generator and use that electricity and distribute it to electric propulsion fans than it is to use a large gas-burning turbine engine, which is used today. And of course, you're reducing the carbon dioxide by over 70%, nitric oxides by over 17%. You're lowering your operating costs. It's safer. You have redundancy. You have less noise. And as you'll see here in a moment, you have the ability to design some really, really cool optimized aircraft because you're not limited to 2 wings, a tail, and 2 big jet engines. So this is a nice graphic just to show you the simplicity of electric propulsion versus turbine engines, which are running at the right on the borderline in terms of temperature and RPM, again replacing them with a simple motor. And so where we're at today is we have electric planes beginning to be sold. Siemens is leading this in terms of the motor propulsion. Aerospace is one of the leading companies that's taking in orders and beginning to deliver these small aircraft that are all electric, battery driven of course. Other developments going on at bioaerospace include even solar powered aircraft. But these small electric aircraft, there's many companies that are headed down that path. There's some new startups that give the promise of a business class style aircraft. So multiple passengers, they claim they'll still be able to do it all battery. We will see how many people and how far they'll go. But what's next? We talked about the futures now. Many of you remember the show The Jetsons, which was in 1962 and portrayed lifestyle in 2062. We're way ahead of George Jetson's predictions. So we don't call them flying cars, we call them something else. And we've actually been working on it for quite some time. Here's in 1906, here's in 1949. And actually here locally on the Space Coast of Florida, at the Florida Institute of Technology, Professor Palmer Stiles was publishing and working on his flying car back in the early 90s. What we call these e-vtols. And this whole concept of a flying car, if you will, or what we call an electrical vertical takeoff and landing vehicle, has been established in terms of an industry by Uber. Uber is investing over $2 billion into this industry. So you no longer just have ride share, you'll have air share. So Uber's plans are to be air sharing around 2023, and they envision by the mid-2030s to be purchasing over 10,000 of these air taxis per year. Now, while they're not designing the vehicles, they're setting the specifications, setting all the standards. For example, it must have at least 4 passengers and a pilot, so a 5-seater to start. There's certain ways that the batteries have to be able to be removable, certain time frame for charging, and they have this all figured out. Their ultimate goal is to be able to move passengers at about 50 cents per mile, driven towards really a distance of 100 to 150 miles and up to 150 miles per hour. So who's going to be in the business? Every major aircraft manufacturer is designing an e-vtol. So let's see what Airbus is up to. And here's a picture of the team that just recently did the tether jump and a snapshot of really what this vehicle will look like when it goes into production. But Airbus even has a bigger vision. Why not associate e-vtol, a flying car, with your actual vehicle? And you'll see in the presentation one more element of this personal transportation vehicle. So why only just fly when you can also drive? Well, let's see what Boeing's up to. Again, very similar to Airbus. These first demonstration vehicles are somewhat of a modified aircraft. This one is not near as advanced as what you saw with Airbus. But again, it's proving out some of the hovering capabilities, propulsion capabilities. This vehicle here is being developed for Boeing by Aurora Flight Sciences. Everybody's in the business. Some of you might know Bell Helicopter. Well, Bell Helicopter doesn't exist anymore. Their new name is Bell. They've eliminated, they've rebranded, no longer Bell Helicopter, and they've changed their logo to a dragonfly, showing the agility of their new vehicles. So very similar to the Airbus vehicle, although this one actually has, as you can see there, it's a quad, but it actually rotates or gimbals these propulsion motors. So again, one thing I want you to really pay close attention to here is that every one of these vehicles has a unique design, has a unique propulsion requirement, and many of these vehicles even have different size motors. That makes AML very happy because developing the technology that we showed you, the permanent magnets, the PM360, we are completely agnostic to what the final solution is. Matter of fact, we can configure that to absolutely meet the specification of every different propulsion motor for e-vtol and these other aircraft and EV vehicles. Embraer, this is an older version of their e-vtol. They have a newer version now that's not public. As you can see in some of these vehicles, you've got the propellers there, which provide the hovering or the lift, and then the propeller in the back there, the propulsion system, is what you call the pusher. And it's not just for people. Another application is organ delivery. And Martine Rothblatt, who has a company called United Therapeutics, which is in the business of lungs and lung disease and refurbishing lungs and delivering lungs and all types of things, she has a vision to solve the organ delivery problem. And you saw the University of Maryland delivering a kidney. Well, delivering some of these organs is a lot more complex, requires a very large payload to maintain, keep the organs alive, etc. And so she has a vision to use e-vtols. So instead of going from a hospital to a courier to an airport, flying to another airport, to a courier to a hospital, her vision is to use e-vtols and go hoppity, hoppity, hop to get organs much quicker to the patient. So she is teamed with Beta Technologies and Kyle Clark for developing these e-vtols. Kyle has recently been in the Wired magazine and he's called the Edward Scissorhands of Flying Cars. So let's see what our friend Kyle is up to.
So this is a 4,000-pound e-vtol aircraft with 8 motors and rotors, and there's 4 rotors in the top that are coupled to one battery, 4 rotors in the bottom coupled to another battery. They're counter-rotating at each corner, and the aircraft takes off vertically with those nacelles pointed 90 degrees towards the sky, and as it rises into the air, those nacelles tilt forward and it starts to accelerate forward. As it accelerates forward, there's a shared lift between the rotors and the wing, and as those approach 0 degrees, you turn into a regular old airplane, and the power comes way down because the lift is being produced by the wing and the thrust is being produced exclusively for forward motion by the rotors.
There's many other eVTOL vehicles being developed. Larry Page from Google has this personal flying device, if you will, that's coming on the market. The volocopter you see on the right-hand side actually flew in 2017, an autonomous flight produced by a German company. I believe it has over 18 motors that lift and propel that vehicle, and that is, as you can see, just a 2-passenger vehicle. And then there's the heavy lift eVTOLs that are coming out. We talked about the Jetsons. Well, you might remember George and his son Elroy. Well, this is Elroy Air, named after George Jetson's son for heavy lift operations. And there are so many eVTOL companies. Quite honestly, there's just too many to count. This is the current list on the eVTOL news directory. And as we mentioned before, at AML, we are agnostic to who wins here. We just want to have our PM360s inside. So let's talk about the larger aircraft. Well, we no longer can just rely on batteries, as we talked about before. So these vehicles are designed with small turbine generators. So you have a small turbine engine powered by a jet fuel or a hydrogen or a biofuel that generates electricity out to the propulsion fans. I mentioned earlier the motivation behind where we went in terms of developing technologies for aerospace, working on this called the M+3 program. Still NASA's dream is to have these large superconducting powered aircraft, but this is a good example showing the turbine generators out on the wingtips, and you can't see that, but on this fixed wing vehicle, there's something like 20 propulsion fans providing the propulsion. And recently they announced some additional funding going to the University of Illinois, still focused on superconducting propulsion, but also on the use of hydrogen as a fuel concept. So let's switch gears now. Let's get back to land. Let's talk about the really futuristic transportation. How do we get, for example, from LA to San Francisco in 30 minutes? Well, we do that by getting in a vehicle that's magnetically levitated, magnetically propelled, right? And we stick it in a tube. It's a concept that we know Elon Musk announced several years ago, but actually Elon, it wasn't his idea. NASA's looked at it for a long time. Matter of fact, since the 1800s, we've looked at putting people into a vacuum tube. So today we have several groups pursuing it, and this is their vision. Being in a vehicle, being in a tube, traveling at 400 to possibly up to 4,000 miles per hour. The company leading this effort in terms of demonstrations is Hyperloop One out of LA. This is their demonstration track, which is located in Nevada. That's a rendering, but giving you an idea of what a finished concept would look like. Other companies such as Transpod out of Canada pursuing the same concept of being in a tube, but using different types of vehicles, different types of propulsion, levitation, and different business models. Most likely, the first use of it will be for cargo before people, but eventually it will be for people. This is a nice rendering of one of many concepts. Reminds us again of transportation is becoming a lifestyle. So it's about the lifestyle, it's not the technology. So as I mentioned, the capabilities, 600 to 4,000 miles per hour. And this is a fun cartoon here asking how LA was. Didn't see it, I blinked. But imagine being able to go over at least 700 miles per hour and being able to get from, again, LA to San Francisco or from LA to Dallas in a very quick way. And then there's some more futuristic concepts that people are working on, which still take that evacuated tube, but now make it a PRT, what we call a personal rapid transit or transport vehicle. So, and then encompassing that as a car and also a drone. So that would be the ultimate PRT vehicle. And other forms of transportation are looking very close to electric and hybrid electric. So these are actually boats that are available and manufactured, which are electrically driven, and some of these are also hybrids. So that's great. We can have an environment where we've significantly reduced the pollution. We have these nice, quiet, efficient cars and trucks and planes, but somehow we have to produce electricity. So while we looked at the energy production and consumption at the beginning of the presentation, we need to think about how we get there in terms of an electrically driven world on the power generation side. So this is a busy chart, but shows you where we need to go on the power generation side, and particularly on the renewable energy side. But you can see here and on this next chart that the cost of electricity, in other words, the levelized cost of energy, the amount of cents per kilowatt hour continues to go down in solar, continues to go down in wind, and many parts of the world have a lot of hydro. So we're really well on our way to have this electrically driven world. And it's interesting to look at some of the major companies like Apple, very large corporation, who also has facilities, data centers, which consume an awful lot of power. And they're making a claim that they are 100% renewable. And even if they aren't fully 100%, even 90% would be very impressive. And you can see here the same with Google. And again, Google has many, many data centers around the world that each consume 5, 10, 15, 20, 30 or more megawatts of energy. And they're able to do that with renewable energy. So that's geotherm, that's wind, that's solar. So the renewable energies exist. We have to continue to harvest them in the most efficient way. And so as we look at this electric, e-mobility and electric transportation, we really need to look at the big picture, the fully integrated approach. And this is a concept that Elon Musk likes to show here. And so this is a house that has solar panel roof, shingles for the battery in the garage, for the electric vehicle. And something else that's happening is that researchers are already being able to produce in labs, not at full production scale yet, but actual windows that are completely clear. And you can't tell, but that's actually a solar panel. So the other aspect that you hear about is that when we look at renewable energy, we have the challenge of energy storage. If we're going to generate energy at night, and be it wind, or be it in the ocean, or even generate it in the day and not be able to use it all, how do we store that energy? And it's always been thought of, if somebody could come up with a solution, that would be the holy grail. It's actually most likely going to take care of itself, because if you have hundreds of thousands and 10,000s and 100,000s of cars, for example, that are out there running around with batteries and being charged at night, you kind of have that built-in energy storage. So having a smart grid and having a large concentration of electric vehicles with batteries is probably going to help solve that energy storage problem on its own. So again, this is where we are today, these highways that have become parkways. And we have a nation here in the US where our infrastructure is falling apart. And this is a study by the American Society of Civil Engineers showing that by 2025, we need about 4.5 trillion to address roads, bridges, and dams. So that's a lot of money. And what is the impact? The impact is significant in GDP, significant to business, jobs, and actually the cost of families. So the ideal situation would be, yes, we need to address the infrastructure, but do we want to fix old bridges, fix old railroad tracks, or do we want to invest in new transportation that's much, much more efficient? Putting our rails above the highways so we get rid of the issue of trying to run trains through towns with crossovers, etc. So this is the future: highways, electric cars, hyperloops, e-vtols, all types of transportation vehicles, again, all electric. And then we have the autonomy. So all of these vehicles we looked at today are going to be, at some point, partially or fully autonomous. So it's a different world. The world is changing. And so for the young people today, they may never have a driver's license. Why would you need a driver's license? In 2019, there are some cities that are already testing Lyft that are autonomous. So you can imagine in the next 5 to 10 years where the autonomous and partially autonomous vehicles are going to be. And one more transportation system that we'd like to look at, something that we call a Skyway system. This happens to be Skytran. Let's take a look at what they're up to. It's a technology that was developed inside NASA. It's now come out and is working on being commercialized.
Burn slower. Traffic is just getting worse, and driverless cars won't save us, because the problem is not the driver, it's the car. It's been a century, and it is time to move on. Skytran is the first public transit system that's as personal as a car. It will unclog our cities and transform our lives. With Skytran, there's no schedule. Its predictive artificial intelligence knows when you need your ride. Stations are so narrow they can fit over sidewalks, so they are always just a short walk away. Skytran's revolutionary magnetic levitation technology enables you to fly on a cushion of air. Traveling in a skypod is so quiet and smooth that you can comfortably work or just simply relax. Skypods don't need to pick up or drop off other passengers, so there are absolutely no stops on the way to your destination. In the city, Skypods can fly over busy streets at 50 miles an hour and speed up to 200 miles an hour between cities. With some stations built directly into office buildings, a 2-hour commute can be reduced to 20 minutes. Skytran's low cost and simple construction allows for many more lines than conventional public transport systems, which in turn allows for greater capacity. Per mile, Skytran is 1/10 the cost of light rail and 1/100th the cost of a subway. With its speed and high capacity, Skytran can bring an end to traffic. A dream come true. The next step will be something we've never even dreamed of. Transforming streets into parks, cafes, and markets. Without cars, we can breathe, create, and wander.
So no end to transportation opportunities. And the other thing that we like about this, as you saw in the video, it's magnetically driven with these magnetic helical motors, and it's magnetically levitated. This is an example of where we can replace over 300 magnets with one single magnet with a PM360 and improve the performance. So what are the takeaways? Transportation is going electric or hybrid electric. E-mobility is the electrification of transportation, replacing engines with motors. Motors are driven by magnets, and so therefore transportation is driven by magnets. At AML, we are reimagining the magnet technology that drives the world. Thank you, and come see us.